Okay, polynomial functions. I usually denote polynomial function by the notation px, even though it is okay to still use fx as a general function. But I use p to emphasize that that's a polynomial. Now, a polynomial function has the pattern of the following: a to the n, x to the n, plus a to the n, a sub n minus 1, x to the n minus 1, all the way down to, let's say, a sub 2 x squared plus a sub 1 x plus a sub 0. Now, the pattern seems to be quite scary, but it's actually not. Don't worry too much. It's just notation. Okay, for example, suppose I have px equals to 5x to the 4th minus 7x cubed plus 4x squared minus 8x plus 9. Let's say I have that polynomial. Now notice that this polynomial is written in descending order. Descending order because the highest exponent is written in the first position. Okay. Now, and when we deal with polynomial, we always write it in that descending order. Is it okay? Now, some terminologies. The first one is that 5x to the 4th, in this case, is called leading term. So if we look back to our general form, then a sub n x to the n is the leading term. Okay, now the leading coefficient is that a sub n. So the 5 here is the leading coefficient. In the general form, a sub n is what we call leading coefficient. Okay, now for the leading term, the exponent is also called the degree. 4 is the degree of polynomial. Now, basically, the leading term is not because it is at the front. No, the leading term is the term that has highest degree. Okay, so among these 5 terms here, this guy is the one has the highest degree, and that's why we write it first. Okay, now, but the reason we call that leading term is because that's the highest degree, and therefore from there we see the leading coefficient, which is the coefficient of that term, and the degree of that term will also be called the degree of the polynomial. Okay, so going back to our general case, then n will be the degree of the polynomial p. Okay, now a sub 0 is the constant. So in this case, the 9, this 9 here is the constant. I think this terminology is not too hard, right? It's okay?
Yes.
Mm-hmm. Now, One thing you can see right away from a polynomial, especially if it is in this general form, is that the y-intercept is 0, comma, the constant. Do you see that? So for this polynomial here, if I ask you what's the y-intercept, then your answer will be 0, 9, right? Just imagine if you plug in x equals to 0, then there will be just the constant part, right? Okay, so one thing that quite easy for us to see later on is that the y-intercept is 0, a sub 0. Again, if they are in that general form, in descending order. Now, let's go on. There are some parts that we need to learn from polynomial. And the thing is, I'm not teaching you only 4.6, but I will also teach you chapter 12 also at the same time. But the one that I think is important for us, what are the things that we need to learn here? The first one is far ends behavior. Second, intermediate value theorem. And then the third one is graphing factored polynomial. Now let's do that one first, okay? And then let's do these three first, and then after that we do more. The intersection later on will be somewhere in between. I need you to have seen that long division and synthetic division. Which I already asked you to watch the lecture videos. Okay, let's start with far end behavior. Now, what is far end behavior? We want to know if we are given a polynomial, let px be a polynomial. We would like to know how the graph of px behaving when x goes to infinity and when x goes to negative infinity. Okay, now it turns out that it depends on. It turns out that it depends on first the degree and second the leading coefficient. Okay, now and this is the far end behavior. Suppose the degree is even and the leading coefficient is positive. Then the far end behavior, the graph will behave like approximately like this, which means when x goes to negative infinity, the y will be going to infinity. When x going to positive infinity, the y also go to positive infinity. As we go far to the left of the graph, of the coordinate system, the value of the polynomial will go to positive infinity. When we go to the right instead, it will also go to positive infinity. Now you can imagine the graph of y equals to x squared. Notice that the graph of x squared looks like this, right? When you go far to the right, it is positive infinity. When you go far to the left, it's also positive infinity. Now, that fact does not change even if I deal with y equals to, let's say, 3x squared minus 100x minus 271. I just do crazy numbers. Yeah, but the graph in general will still, when x goes to positive infinity, when you go very far to the right, it will go to positive infinity. When you go very far to the left, it will go to positive infinity. Okay, now instead of writing too much, I will just summarize that in graphing. I will just call that like this. Of course, we don't know what happened in the middle. We don't know what happened in the middle. Okay, what we know is when I go to infinity, positive infinity, the y value will go to very high. When I go to negative infinity, the y value will go very high also. Now, if the leading coefficient is negative, however, then we make it upside down. Of course, again, we don't know what happened in the middle. Okay, you can imagine what happened if I have y equals to negative x squared. Now, the same thing actually applies when I have y equals to, let's say, negative 4x to the 6 plus whatever minus whatever. As long as the leading coefficient has even exponent and the leading coefficient is negative, then when x goes to infinity, the further x goes to the right, this becomes a very large number. This becomes very large number, okay? And multiplied by negative 4 becomes very negative number. The same argument applies when I use x going to negative infinity. Now, what happens if the leading coefficient is odd? If the leading if the degree is odd. If the degree is odd, then the shape of the graph will be approximately like this. Again, we don't know what happened in the middle. Think of y equals to x cubed. Okay, when x is really large, then the y value gets very large positive also. But when x goes to negative infinity, the y will also go to negative infinity. The further I go to the right, I will go up. The further I go to the left, I will go down. Okay, now again, we don't know what happened in the middle. But at least we know what happened when you go very far to the left or very far to the right. Now, when you have the leading coefficient is negative, you basically make it upside down. Which means if I go very far to the left, the value of y will be positive infinity. When I go very far to the right, it will be negative infinity. Okay, so if we look back to the polynomial we have above here, if we look back to this polynomial, the leading coefficient is, leading term is
5x.
5x to the fourth. Okay, so the degree is even, and the leading coefficient is positive, right? Okay, so when we graph that later on, it will follow, the shape will be approximately like this. Something happened in between, but then very far to the left, it will be going to positive infinity. Very far to the right, it will be going to the infinity also. Okay, now if we have a chance, we'll graph that later on. That's for how to apply this leading coefficient. Now, our main goal for this section is, for this lecture today, is to graph polynomial functions. Now, the next thing is intermediate value theorem. Intermediate value theorem. Okay, let me go back a little bit. Here. Okay, now, if you look at this polynomial function, and actually every polynomial function, what is the domain?
Positive infinity, negative infinity.
From negative infinity to positive infinity, basically all real numbers, right?
Yeah.
Okay, basically all real numbers. Now, but how about the range? Notice that when the n is even, if the degree is even, then they will have the same positive infinity or the same negative infinity. So what will happen is, if the degree is even, the range will not be all real number. Okay, well, think of it like for example, y equals to x squared. What is the range?
0 to infinity.
From 0 to infinity, basically not all real numbers, right?
Yes.
Okay, now, but then when the degree is odd, you see that it's from negative infinity to positive infinity, negative infinity to positive infinity. In other words, once we know that the degree is odd, then the range is all real number. Okay. Now, another good property of polynomial is that it is continuous everywhere. Now, intermediate value theorem that I use here, I modify that to be for our polynomial functions, but actually applies to every continuous function. So what it says, let fx be a continuous function and notice that polynomial is a continuous function. Melis?
Yeah.
Mute your microphone, please. Now, then, suppose fx is a continuous function, then if a is not equals to b and f a fb has opposite signs. I'm sorry, I actually don't need this statement here. Then if fa fb has opposite signs, let's say, for example, f3 is 10 and f4 is -3. Let's say like that. Okay, when I say opposite sign, it refers to positive and negative. Okay, now then there is a C between x equals to a and x equals to b such that FC equals to 0. Okay, now here's the illustration. I will continue using this example here. Now imagine on the coordinate system, okay, F3 equals to 10, F3 equals to 10, and F4 is -3. So it's below x-axis. Now the thing is, for me to move from 3, 10 to 4, -3, for me to move from 310 to 4, -3, I must cross x-axis. Is it right? I must cross x-axis. Okay. Therefore, as long as FA and FB has opposite signs, then there must be a C between 3 and 4. There must be a number between 3 and 4 such that that number is the 0 of the function. That's what intermediate value theorem says. Okay, actually intermediate value theorem says something more general than this, but I just use the part that we will use later on. Okay, so let's say, for example, another better example, I believe, let's call that a formal example right now. For example, fx equals to x squared minus 2x minus 3. Notice that f0 is f0 is -3, right? And how about f4? f4 is 4 squared minus 2 times 4 minus 3, that's 11, that's equals to 5. Notice that f0 is negative, while f4 is positive. Because they're opposite sign, then we conclude there must be a 0 between, there must be a 0 between x equals to 0 and x equals to 4. Okay. In fact, we know that this function, this quadratic function, is factorable. X minus 3, x plus 1, right? So the zeros are x equals to 3 and x equals to -1. Notice that this this 3 here is actually between x equals 0 and x equals to 4. You see what I mean? When I try to graph that, let me roughly graphing it. It looks like this approximately. Notice that my f0 gives me -3, and my f4, my f4 gives me +5. And somewhere in between, the graph actually cross x-axis. Okay, now, so intermediate value theorem says that if FA and FB have opposite signs and the function is continuous, then there must be a 0 in between. Now, it doesn't say that there must be only one 0. There could be more than one. It just says that there must be a 0 in between. That's one. What happened if FA and FB have the same sign? then we will say no conclusion, because intermediate value theorem does not say anything. Does not say anything in that situation. And actually, we cannot conclude anything from just that, because what? Imagine if I have a coordinate system here, and one point is above x-axis, another point is above x-axis. It is possible the graph just goes straight right away, zoom. So there's no x-intercept, right? But it is possible that you happen to choose 2 points, and in between you have 2 x-intercepts. Do you see that? Okay. So it is possible that if they have the same sign, they still may have zeros in between. Nothing can be safe. You know, it is possible nothing, it's possible something. So in case that they have the same sign, then we don't know. Intermediate value theorem does not say anything about that. Okay. We will save this at the back of our mind. We'll save this at the back of our mind for now. Next thing that we will do is graphing polynomial factor. Graphing, to be more precise, linearly factored polynomial. Now, Thomas, what do you mean by linearly factored polynomial? Let's say, for example, we have px equals to x plus 3 x plus 1 squared and x minus 4 cubed. Let's say I have something like this. And I want to compute this. You know what? Do me a favor. Erase that 4, change that 4 becomes 1. So change that 4 becomes 1 for sake of computation. Well, because it is polynomial, then the easiest question possible is, what's the domain? The domain of polynomial
all real number.
That's all real numbers, that's right. Now, slightly harder in this case, what's the y-intercept?
-3.
1.
Negative.
-3, that's right. To be more precise, it's 0, -3. Okay, just plug in when when x equals to 0. So when x equals to 0, you get 3 times 1 times -1. Right? Okay. Now, I mean, including the exponent, that's what you get. So 3 times +1 times -1, that's -3. That's the y-intercept. Now, how about the x-intercepts?
-3, -1.
Almost right.
Negative 3, 0.
-1,
1, 0.
-1, 0. And then 1, 0. In fact, we can say more that -3, 0. So the zeros are -3, -1, and 1. For -3, the multiplicity is 1 because the exponent is 1. What is the multiplicity of -1?
2.
2. What is the multiplicity of 1?
3.
3. Okay, now then why do we want that? Because then when we try to sketch the graph later on, knowing the multiplicity of zeros actually helps. Before I actually sketch them, let me do the sine graph first. Or how about you doing the sine graph? Let me ask you to do the sine graph. So let's say I have a number line here, and then I have -3, -1, and 1. Those are the zeros, so don't forget this. I plug when x equals to -3, the y is 0. When x equals to -1, the y is 0. When x equals to 1, the y is also 0. Okay, then what's the y-intercept again? Y-intercept is -3, which is negative here, right? I just need the sign. Is it okay? Now you will see the following. 1, this 1 here is a 0 with odd multiplicity. 1 is a 0 with odd multiplicity. Now, if that number is a critical number with odd multiplicity, then when we jump across that critical numbers, we will change the sign. In other words, a 0 with odd multiplicities must have opposite signs on the left and right hand side. Of course, you can also try that though. It's like, let's say when you get x equals to 2, then you plug it into the polynomial, then 2 plus 3 times 2 plus 1 squared times 2 minus 1 cube, right? This is positive squared, this is positive cube. Well, everything's positive, so it's positive anyway. Now, but that's actually, what I want you to see is like, you know what? We don't really like to use this method anymore because it's too primitive. We have a better method right now. The better method is looking at the multiplicity of the 0. Okay, if the multiplicity is odd, then the sign will change. If the multiplicity is even, like at -1, then the sign will stay the same. Okay, when at -3, the multiplicity is odd, so when we jump across the critical number, then we will change the sign. Now that's the Sine graph. Now, what does it mean? It means when we try to graph that later on, when I try to graph that later on, then my graph will be up and down across the x-axis based on those numbers. So at -3, this is -3, this is -1, this is 1. Okay, then the y-intercept is 0, -3, let's say approximately here, and then the far end behavior will be positive, I mean infinity to infinity. So I will come from here, go down. You see, between -infinity to -3, that's positive. That's above x-axis, right? Okay, and then between -3 to -1, that's negative. It's below x-axis. It's below x-axis. Now, how about between -1 to 1? That's still negative. So it's still below x-axis. Now then, from 1 to infinity, it's above x-axis. Okay, so using the plus minus, we now then know, is it above or below the x-axis? If the sine graph is positive in that interval, it means it's above x-axis. Below x, if it is below, then the sine graph will show negative. Any question? If you have no question, I give you an example, another example that I would like you to sketch the graph. At least do the sine graph. Do the sine graph and then try to sketch what the graph looks like. For example, if I get px equals to -2 times x minus 3 times x minus 1 cubed times x plus 2. I want you to answer. First one, the easiest one. A, what's the domain? Part B, what's the y-intercept? Part C, oh, you know what? What's the degree? And leading coefficient, therefore you will get the leading term. And then find what's the far end behavior. You can use notation like this, like this, like this, like this. Or sometimes in my old solution, I say infinity to infinity, negative infinity, negative infinity, negative infinity, positive infinity, or positive infinity, negative infinity. That's for the far end behavior. And then after that, I want you to get me the zeros with the multiplicities. And then the sine graph. Maybe this 6 question first. Let me give you 5 minutes from now. The domain will be all real numbers. How about the y-intercept? 0,
6.
no, it won't be 6. I don't think it is.
-12.
-12, that's right, -12. And what is the degree?
5.
5. The leading coefficient?
-2.
So the leading term is -2x to the 5th. Now, what is the far end behavior then?
I don't get it. How come the degree is 5?
I'm sorry, Malis, it's not that clear. Speak directly to the microphone.
How come the degree is 5? I don't get it.
Oh, the degree is 5 because of this. You see, this is degree of 1,
Oh,
degree
yeah.
of 3, degree of 1. Okay. Okay? Mm-hmm.
Yeah, thank you.
Sure. Well, how about the far end behavior? Which one will that be? The first, second, third, fourth. Which one is that?
So you multiple with x minus 1 the whole cube with 2 to get a leading term?
With -2.
Oh, with okay.
Yeah, so it's like -2 times x cubed times x.
Okay.
Right? Okay, so the far end behavior will be infinity to negative infinity. In other words, later on when we sketch the graph, we will see on the far left it will be positive infinity, will be positive sign, and the far right will be negative sign. Now let's do the zeros with multiplicities first. What are the zeros?
3,
3 with multiplicity of
1.
and
1 multiplicity 3.
1 with multiplicity of 3, and then negative 2 with
Negative
multiplicity
2.
of 1.
Multiplicity.
Okay, now therefore the x-intercepts will be 3, 0, 1, 0, negative 2, 0, and the sine graph, let me do it underneath. Part F, the sine graph, negative 2, 1, 3. This is positive, 0, 0, 0. This is negative. Do you know why I know that on the far left it's positive and far right is negative?
Oh,
The end behavior.
The far end behavior, that's right. Now, even if you don't do that first, you can do it from the middle. For example, the y-intercept is when x equals to 0, the y is negative 12, right? Okay, and then from here, when you jump across negative 2, the multiplicity is odd here. So you change the sign. When you jump across 1, the multiplicity for 1 is what?
3.
3. So it's odd, I
Check.
still change the sign, right? And then multiplicity for 3, that's 1. It's odd, I still change the sign. Okay, so you can use the far end behavior to help. You can use the y-intercept to help. You can use the combination of both. Okay, but using the y-intercept to help may not be useful if the y-intercept happens to be 0. So it doesn't tell us the sign, is it positive or negative? Now, in that case, then you may get better by using the far ends behavior. Of course, don't forget you can always use the primitive way. For example, you choose when x equals to 5. What's the sign, right? When x equals to 5, then negative 2 times negative 5. I'm sorry, negative 2 times 5 minus 3 times 5 minus 2 cubed times 5 plus 2. And then you compute, oh, I get negative very big numbers like that. Okay, that's the worst case though. That's the worst situation. But at least using the multiplicity of the zeros, we can get the sine graph a lot faster. Now then, how do we translate that to the graph? Suppose this is our coordinate system. Okay, that's our coordinate system. The y-intercept is negative 12. You know what? Let me do the x-intercept first. Negative 2, 1, and 3. Okay, now negative 12 will be very far down here, quite far down here. That's 0, negative 12. Okay, the graph then will go from positive infinity, use our power, from positive infinity, go down to negative 2. Actually, we can say more. Notice that the multiplicity at x equals to negative 2 is what?
1.
1. So when it crosses that x-axis, it will cross linearly. It's just like very quite straight. Okay, and then going down further, let's say it goes up here. What is the multiplicity of 1?
3.
3. So when it crosses that 1, it will behave like an x cube. It will behave like an x cube. And then at 3, what is the multiplicity?
1.
1. So it will cross straight like that. So from here, you see that because it crosses straight at this 0 and this 0, then we know the multiplicity is 1. Okay, and because it crossed the x-axis here, but it's not crossing straight, then multiplicity must be odd and greater than 1. if I look back to the previous graph,
I have a question.
I think he get disconnected.
okay, sorry. I think I lost connection earlier. It's from me. Now, yeah, that's about graphing factored form. Now,
I have a question real quick.
yes,
How do you determine the values in between the zeros? Are you just like estimating them, or just you don't care?
estimating the values. All I care is actually is it positive or negative.
Okay.
Yeah, that's all. Okay, because if you want to put more details, then it's just about how far up you go and how far low you go.
Okay.
But for now, we don't really worry about that.
Okay.
Once you go to calculus, then one of the things you need to do there is finding what is the maximum here and finding where the minimum happened here. You see what I mean? But that's when you go to calculus. The worst way to graph this is actually you plot one by one, like when x equals to -5, -4, -3, -2, so on and so forth. Okay, but no, it doesn't give you the feel of what the graph actually look like. I mean, that's the way you. If you do it this way, you basically learn nothing. Okay, yeah, but your good question is this: how do we know how far do we need to go up or how far we need to go down? We don't do that yet here. Okay. In calculus, then you will see then it will go how far it should go up here and how far it goes down here. In fact, I think I need to say something there that actually I don't know if it will cross on the, it will go down first and then cross from -12 from below, or either it goes this way. I don't know. It may go this way instead, right? Okay. I don't know. Actually, we don't know that at all. But all I know is like eventually it will cross, it will have a y-intercept somewhere in between, right? It will have a y-intercept 0, -2, and then goes up to 1, where it will cross that like an x cube, and so on and so forth. Okay, now, so to conclude this part here, which is basically the end of 4.6,
Yeah.
To conclude 4.6, and I will go to chapter 12 from here. We know that we can graph px if it is linearly factorable, linearly factored. Now, so if the polynomial is not linearly factored, if the px is in general form, the one that I showed you earlier, the descending form, 5x to the 4 and blah, 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 right? Now, then we need to factor. Okay, so the rest of the today's lesson is basically dedicated to finding methods, learning to factor a polynomial with degree 3 or on. Okay. Unfortunately, there's no single tool, there's no single method, there's no single theorem, single rules that we have to fully factor a polynomial. However, we have plenty of theorems that helps us to identify the factors. Okay, now notice that for us to do the factoring, let me go back a little bit here. For us to be able to factor it, I was referring to this, for us to get this form here, okay, one thing we do will be later on to find the zeros. Okay, one thing we do is to find the zeros. So you will see in the next 1 hour or so, what we do in this lecture is basically learning all the tools we have to find the zeros, and therefore we will be able to fully factor the polynomial later on. And there's still a chance that we find a polynomial that we cannot factor at all. Okay, now, but what are the things we need to know here? First one, long division, syntactic division. I will do one example for long division and maybe 2 examples for syntactic division. For example, suppose I want to divide 3x to the 4th minus 2x cubed plus 5x squared plus 3 divided by x squared plus 2, let's say. We can use long division for every type of division for polynomial. Like if you have a polynomial divided by a polynomial, you have a polynomial on the top and divided by a polynomial at the bottom, you can always use long division. Now you will see later on, syntactic division can only be done, at least at our level. We don't have time to do the variation. Syntactic division can only be done when be applied when the divisor is of the form x minus c. Basically, it has to be linear with coefficient 1. Okay, but if you have degree of 2 at the bottom, degree of 3 and all, we have to use long division. Now, how to apply the long division? Now, the numerator will be on the top. The denominator will be at the bottom. Now, especially when on the numerator, if you see a skip, let me show you, I have a skip here. If you have a skip of exponents, this is supposed to be degree of 4, degree of 3, degree of 2, and then degree of 1, and then constant, right? You see that I'm missing degree of 1. Okay, now if you have that situation, then you need to insert a placeholder. Insert a placeholder plus 0x plus 3. Okay, now we call this guy here a placeholder. Okay, now let's start with the division. X squared times what give me 3x to the 4? X squared times what give me 3x to the 4? that is 3x squared, right? Okay, so I will put 3x squared here. The reason I put here because it's the same place value. Okay, now then I will distribute this 3x squared to x squared and the 2. That will give me 3x to the 4 plus 6x squared. Then I will subtract. Of course, when I subtract 3x to the 4, it's supposed to cancel. Okay, and I have 2x cubed plus or minus here for the x squared term.
It's not plus, it's minus.
Repeat again.
It's minus 6x squared.
Minus what?
She said minus x squared.
Yeah, minus x squared, and it's minus 6x squared.
Yeah, minus 6x plus 5x squared. So it will be minus x squared.
Minus
No?
x squared, that's right. So because what? Because we have 5x squared, we
Minus,
have this 5x squared minus, right?
yeah.
6x squared, that's how we get that negative x squared. Okay, now then we will repeat the cycle again. We repeat the cycle, x squared times what? X squared times what give me negative 2x cubed.
Negative 2x.
Negative 2x. Now the place value for negative 2x is here, negative 2x. And then I distribute that negative 2x to the divisor. It gives me negative 2x cubed minus 4x, right?
Yeah.
And then I subtract. I will get negative x squared and then
5, no. Negative. So
0x minus negative 4x is positive 4x, right?
yeah, positive 4x.
Plus 3. Now then we will repeat the procedure again. We repeat the procedure again. Let me use green color right now. X squared times what give me negative x squared?
Negative 1.
Negative 1. So I put negative 1 here. This will be negative x squared minus 1, which when I subtract, it gives me (4x plus 4). Okay, now then you actually don't need to show me this though. The box here, you don't need to show. You don't need to show me, but I show you because otherwise you ask me more questions, right? Okay, now so after I divide that, what's the quotient? Then the quotient will be 3x squared minus 2x minus 1 plus the remainder over the divisor.
Question.
Question, huh? Go ahead.
Weren't you supposed to multiply negative 1 by 2?
Yeah.
Oh yeah, that's right. Who wrote that negative 1?
It's negative 1 by 2. It's gonna be like
So my bad. This should be like this, right?
Yeah.
Okay, so let me write it as a correction then, instead of just erasing it. It should be 5 here. So it should be 5 here. Is it okay now?
And one more question.
Uh-huh.
So I was reading the textbook and they said you know you're done when your remainder is 1 degree less than the
That's right. Uh-huh. That's right.
Okay.
Yeah.
Okay.
Once the terms that you are going to you're dealing with is the terms that you have here is degree of 1, right? Which is less than degree of 2, then you know you can stop. Okay? Yeah, we stop when the remaining degree is less than the divisor. Now, how about synthetic division? Synthetic division is done only when the divisor is linear. So synthetic division only when you have a polynomial divided by x minus c. Of course, the c may be a negative number. Okay, a polynomial divided by x plus or x minus something. Let's say, for example, if we have 4x cubed plus 5x squared minus 7x minus 4, all divided by x minus 2. So what is the c here? What is the c here? The c is 2.
Yeah.
Okay, now the way synthetic division being done is we will do this kind of box. We have 3 rows in this box. Let me write it this way. We have 3 rows in this box. There will be 3 rows in this box. Okay, now on the first row, you will insert inside the box the coefficients of the px in order, in descending order. And be aware if you happen to have any skip. Now here it's degree of 3, degree of 2, degree of 1, and constant. Okay. Now then, in the second row, you will insert, outside of box the c. In this case, it's 2. So far, so good? Now, the procedure for synthetic division will be done in the following way. First, the first coefficient here, the leading coefficient, will go down, will be copied down here all the time. And then 4 times 2, whatever the product, you put it here. What's that? That's 8. And then when you add, you get 13. Is it okay? Now, I will repeat the procedure. 13 times 2 is what?
26.
Then I will put it here. And then I add. And then I go the procedure again. 19 times 2 is
38.
38. And then I add, that will be 34. Now the last number, you will box it, a smaller box.
One question.
Uh-huh.
Is there like a really in-depth explanation of why you dropped the first term besides it's like 1 degree lower?
Well, because 4x cubed divided by x must be 4x squared,
Okay, all right.
right?
Yeah, thank you.
Okay.
Yeah.
Now then, we are actually done with the syntactic division. We need to just reinterpret it back. Now, because this is degree of 3, then the quotient will be degree of 2. We divide by a linear, right? Degree of 1. So the quotient must be degree of 2. So it will be 4x squared plus 13x plus 19. Okay. Now I box the 34 there because that's the remainder. That's plus 34 over x minus 2.
I was missing a little bit. Can you explain again?
Which part?
Like how you got 26 and 38?
Okay, let's just I start from the setup then. Okay,
Yeah,
the
thank you.
setup was like this, right?
Mm-hmm.
Okay, now the first number always go down. This is all 4.
Okay.
Now multiply 4 by 2.
8,
8. Now you put that 8 under 5. And then you add.
13.
Now do the same procedure again. 13 times 2.
Oh, okay. 26.
Now you put it here. And then you add again.
19.
And then do the same procedure again.
38.
Uh-huh.
34. Okay.
But the last column, the corner, you box it out.
Okay.
Now, then this 4, 13, 19 in that order give us the coefficients. 4, 13, 19 give us the coefficients here.
Okay.
And
Thank you.
then the constant inside the box will be the remainder.
Thank you.
Okay, sure. Now, I would like you to practice one example. Let's say I have, for this example 2, if I have 3x to the 5th plus 5x cubed minus 7x minus 1, all divided by x minus 1. Maybe, how about if I change that to be plus 1? And I make it plus 1 also here. I change this one. I change this. It was negative. Now I make it plus. Okay, try this. Okay, let me start. That will be inside the house on the first row. 3,
3, 5,
0,
0,
5,
5, 0,
negative
negative 7, 1.
1.
Don't forget the placeholder, okay? We need
Oh.
that placeholder. You have a skip, right? You have a skip here. You also have a skip there. Now then, what number do I use outside?
Negative 1.
Negative 1. Now then I do the procedure 3 times negative 1 is negative 3. When I add negative 3, this becomes 3 here. This is 8, negative 8, negative 8, 8, 1, negative 1, 0. So the quotient will be 3x to the quotient will be 3x to the what?
Five.
That's the original question, degree of 5.
4.
Degree of 4, that's right. 3x to the 4 minus 3x cubed plus 8x squared minus 8x plus 1. Supposed to be with plus 0 over x plus 1. But of course, we can omit that because it's already 0. You see what I mean? Okay, so I will just erase that because the remainder is 0. Now, that's long division and synthetic division. For now, you have to be very strong with synthetic division. Okay, now why do we need that? You will see that that's our tool. You will see that tool right away in the next theorem. The next theorem that we will deal with, two important theorems. First one called remainder theorem. And factor theorem. In fact, if I take a look in our book, this is actually 12.3. This is 12.3. And what we did earlier, long division, syntactic division, this is actually 12.2. Okay, what is the remainder theorem? Remainder theorem says the following. Oops, sorry. Remainder theorem says the following. If polynomial px is divided by x minus c, then the remainder, which we usually call R, is equal to PC. Okay. Suppose I will show you the proof. Suppose the quotient is denoted by QX. Okay, so PX divided by x minus c is equal to QX plus remainder over x minus c. Now, let me quote the example we have earlier. This one. So this is my px. This is my px. This is my x minus c. This is my qx. And this is my remainder. Sorry. This is my remainder. Okay, so polynomial, my polynomial px here, divided by x minus c, give me the quotient qx with remainder r, and this is still x minus c, right? Okay, now I just try to show you that like when we divide px by qx, then we will have the quotient qx, px divided by x minus c, then the quotient is qx, and the remainder r over x minus c. Now, imagine from here, I multiply by the LCD, x minus c. If I multiply by x minus c, then I get px is equal to qx times x minus c plus r. Are you with me? Now, so when I set x equals to c, then I get pc equals to, this guy will be 0, right? Plus r. Therefore, pc equals to r. Let's try to take a look in this example here. So 4x cubed plus 5x squared minus 7x minus 4 is equal to x minus 2 times 4x squared plus 13x plus 19 close parentheses plus 34. Now, if I call this my polynomial, if this is my polynomial px, then p2 will be, this will get to 0, right? And I have the constant left. Okay, how do we use this remainder theorem? I'm about to give you a break, but hold with me a little bit. Suppose, for example, I have px equals to 3x to the 4th minus 5x squared plus 7x plus 4. And I want to find out what is p2. Okay, now the first method that we have learned before, P2, you plug in 2 in. You plug in 2, replacing the x by 2. Right, that's the way we did it. Right, okay, but now we have a better method. The better method is you do synthetic division, the polynomial 3, 0, negative 5, 7, 4, and you put 2 here. So P2 equals to 46. Now, that's one of the big use of remainder theorem. Okay, so if you want to compute P1/2, for example, instead of plug the 1/2 into that polynomial and get a lot of fractions, what you can do, you do the following. You plug into, you use synthetic division and look at the remainder. The remainder is the value of P1/2 if you use 1/2 instead. Okay, it's 6:08 right now. Let me give you a break. We come back at 6:20. We come back at 6:20. My break is a bit too late. That's for remainder theorem. One of the big use of remainder theorem is to help us finding the value of a polynomial at certain x. That's actually one of the big use. Don't forget that this is actually quite useful also when we apply intermediate value theorem later on. Now, let's go back to the discussion. The second part of this section is factor theorem. Factor theorem is actually the continuation of remainder theorem. Factor theorem says the following. If Px is divided by x minus c and the remainder equals to 0, then q and then x minus c is a factor. Of Px. Idea, or kind of like quote unquote the proof. We know from the division algorithm, Px divided by x minus c equals to qx plus r over x minus c. That's something we have earlier. I just quoted again. That's something we have here. That's what we have here. That's what we have here. Okay, now then continue. If I multiply by x minus c, therefore, if I multiply by x minus c, therefore, I have Px equals to x minus c times qx plus r. Okay, that's still remainder theorem. That's still remainder theorem. Now, factor theorem says the following. Suppose r equals to 0. Suppose r equals to 0. Then what happened to the polynomial Px equals to x minus c times qx, right? If r equals to 0. Now then, from this expression here, we can see then x minus c is a factor of Px. No remainder, right? No remainder. So x minus c times something give us px. Basically, from here, then we see the following. If the remainder equals to 0, but at the same time, that's equals to pc, then x minus c is a factor. Is it okay? If c is a 0, if c is a 0, this basically c is a 0 of px, or pc equals to 0. It means x minus c is a factor. Okay, and from there we can also say that c comma 0 is an x-intercept. Of course, if c is a real number. Now, you have to remember this though. You have to remember this because we have known that if c is a 0 and c is a real number, then c comma 0 is a factor. If c is a 0, then c comma 0 is an x-intercept. That's something we learned even before this section. Now, what this section saying, this factor theorem saying is actually that if you have a 0, then c is a 0, then x minus c is a factor. Okay, now, but if we look back even further, if x minus c is a factor, it implies qc also a factor. Right? Okay, now let's do some example. I want you to read more than what our text, what the theorems on says. Suppose, for example, I have this polynomial, px equals to, let's say, x cubed minus 4x squared minus 9x plus 36. Okay, and somebody say that, you know what, -3 is a 0. Now, once I tell you this little secret here, then can you factor the polynomial? And therefore, once you are able to factor it, we will be able to graph it. Okay, hold on, Thomas. Hold on. What is the degree of this polynomial?
3.
3. How many zeros we have right now?
1.
1. How many zeros we supposed to have?
At least 3.
Actually, exactly 3.
Oh,
Okay.
yeah.
According to the fundamental theorem of algebra that we'll see very, very soon, and it's just that short, that the number of zeros a polynomial should have is equal to the number of equals to the degree. So if the degree of that polynomial is 3, then that polynomial must have 3 zeros,
Even complex zeros?
including complex zeros. Okay, yeah. So now, but right now I have only 1 0. How can I factor this polynomial and therefore graph that? Once I am able to fully factor this polynomial, I will be able to graph that, I know. But how do I fully factor this polynomial with only 1 0? Well, telling us that -3 is a 0 enable us to reduce the polynomial. So 1, -4, -9, 36, -3 here. And then This is 1, -3, -7, only 1. And what is this? 12,
Well,
-36, 0. Okay, so we know that -3 is a 0. Why do you do that, Thomas? We do expect that the remainder will be 0, right? Why? Because they tell us -3 is a 0. When they tell us -3 is a 0, it means, let me write it as a note here. It means P -3 is a 0, is it right? So we do expect that this part is supposed to be 0. Okay, so Thomas, why do you do the syntactic division? Because I use that x equals to -3. I know I will have x plus 3 as a factor. But what is the other factor? X squared minus 7x plus 12. Now is a quadratic, right? It's the degree of 2, it's quadratic. Then
Yes.
from there, we can factor it, or if you cannot factor it, you can use completing the square or quadratic formula to find the zeros further, right? But I believe on the one we have here is factorable. So x plus 3, x minus 4, x minus 3. Is it right?
Mm.
Now, then from here, we actually get all the zeros already. The zeros are x equals -3, x equals to 4, x equals to 3, and all of them have multiplicity of 1. Right? Now, once we get the zeros with the multiplicities, remember we can do the sine graph and then the graph. Okay? So we can already factors, then you do the sine graph, and then you do the sketch of the graph. Okay, now that's what the factor theorem for. Factor theorem, once you know a 0, you use, then you know a factor. Using that factor, you can find the other factor. Because -3 is a 0, then x plus 3 is a factor. Because x plus 3 is a factor, then the quotient must also be a factor. Because the quotient is a factor, then I can go on further. I basically already reduce the polynomial from the degree of 3, now becomes the degree of 2. Now I reduce that further. Now because it's the degree of 2 already, I can use factoring, completing the square, or quadratic formula to find the zeros, and therefore get the factors again. Okay, now that's for factor theorem. Let's list what we have learned so far, by the way, otherwise we kind of lose track. We have learned var n behavior. That's easy, that's memorizing, but I hope after doing it for a while you have some good feeling about it. And second, we already learned intermediate value theorem, but you see that we just learned a little bit of var n's behavior. We only learned a little bit of intermediate value theorem, and from there we learn long division, synthetic division, and then after that we learn remainder theorem with factor theorem. Okay, now we have more theorems to learn. The next theorem we'll learn will be fundamental theorem of algebra. That's very short, but our textbook call that one section. And then after that, I will teach you rational zero theorem. After that, I will teach you, oh, Thomas, so much. Yes, that's a lot. After that, I will teach you Descartes' rule of sine. the most precise rules of sine. And then the last one, conjugate zero theorem. Fundamental theorem of algebra is easy. Conjugate zero theorem is short. We still have two more theorems called boundedness theorem, but I will not teach you that because it's not super important anyway. Eventually, you have a good feeling on that, and I can teach from that boundedness theorem along the way when we do problems. Okay, now what is fundamental theorem of algebra? First, fundamental theorem of algebra is something you see in 4.4. Fundamental theorem of algebra. Fundamental theorem of algebra says that a polynomial px of degree n has n roots. Counting multiplicity, and complex. Complex roots. Now, how do we use this fundamental theorem of algebra? This fundamental theorem of algebra help us answer one fundamental question. Okay, how many roots px has? The answer is n. Depends on the degree. Okay, so in other words, if I look back to this polynomial here, the degree is 3, right? Okay, the degree is 3. So once I get 3 zeros, I know I can stop. The number of zeros a polynomial has should not be more than the degree. Okay, so suppose I already answered this question, right? Okay, I already answered this question, and I say, oh, the zeros are -3, 4, and 3. Then if somebody asks, how do you know there are only 3 zeros? How do you know that there's no more other numbers that satisfy this that are the zeros of this polynomial? And your answer will be, well, because fundamental theorem of algebra says polynomial degree of 3 must have only 3 zeros. Should not be more. Okay? That way we know when to stop. That's for fundamental theorem of algebra. I think that's quite easy to memorize. How many zeros a polynomial have? Basically look at the degree. That's it. Okay? So if you have a polynomial of degree of 4, polynomial with degree of 4, then if we need to find the x-intercepts, then it must have at most 4 x-intercepts, at most. Maybe less, because you may have complex roots. Okay, now that's for fundamental theorem of algebra. I may jump right away to conjugate zero theorem. I don't know what section is that, but because it's so short, I can just mention it right away. Conjugate zero theorem. Conjugate zero theorem says the following. If a plus square root of b is an irrational or complex zero, of px, then a minus square root of b is also a zero of px. Now, we already seen this phenomena in the past, but let me remind you what's that. Suppose I have this px. Let px equals to x squared minus 6x plus 3. And I want to find the zero. So I set that equals to 0. So negative 3 equals to x squared plus 6x. What number should I add? 9. So negative 3 plus 9 equals to x squared minus 6x plus 9. 6 equals to x minus 3 squared. When I apply square root property, I get plus minus square root of 6 equals to x minus 3. So x equals to 3 plus minus square root of 6. Now you see that the solutions x1, x2 are conjugate to each other. Okay, in other words, if 3 plus radical 6 is known to be a 0, then the conjugate, which basically you have the same number, okay, the same number here, but opposite sign here. You see that? Okay, we call that conjugate. Of course, the blue part here, radical 6, has to be irrational. Okay, it has to be irrational. Now, so once you know one irrational 0, then you know the conjugate also a 0. Okay, that's the intuition. Now, suppose for example, I tell you that radical 3 and 2i are zeros of a polynomial px. Implicitly, then, we get that buy one, get one free. Buy two, get four. Okay? Buy one, get one free. Buy two, get two frees. Okay? Because radical 3 is an irrational number, then the conjugate must also be a 0. Right? Okay? Because 2i is a complex number, then negative 2i also a 0. You see what I mean? They only give us 2 zeros, by the way. But using conjugate zero theorem, then I get 2 extra zeros. Then from here I see this polynomial must be degree of, at least degree of 4. Right? Because we know 2 zeros, but both of them irrational and complex. Because we have 2 zeros, one of them irrational, so the conjugate also 0. The other one is complex, therefore the conjugate also 0. But this means we now have how many zeros? We have 4 zeros, right? Because we have 4 zeros, then from there we know four zeros known. There could be more zeros that we don't know, which implies px must have a degree of 4 or more. Okay, that's what conjugate zero theorem is saying. So again, it's supposed to be that simple. If you get confused, you must be thinking too hard. If you know a zero that's irrational or complex, then the conjugate must also be zeros. That's it. Now, the next one is rational zero theorem. Of so many theorems we talk about here, rational zero theorem is one of the most important theorem. What it says that let C be a rational zero of polynomial Px. So this talk about a rational zero. The previous theorem talk about irrational zero and complex. Now, if C is rational zero, what does rational mean? C is rational means you can write that as a fraction. If C is rational, then C can be written as a fraction. Okay, now if let's C be a rational zero of Px and the coefficients of Px, Ai, are integers. The coefficient of Px are integers. Then C must be plus minus of a factor of the constant term over a factor of the leading coefficient.
Question.
Uh-huh.
So I went over this a couple of times.
Hmm.
Why not the other way around? Why not AN on top of A naught? Curious.
Let's see if we have this zero. If x equals to 2 over 3, and then let's say the other zero is 1/2, then it must be 3x minus 2 equals 0, and 2x minus 1 equals 0, right?
Mhm.
Okay, which means the polynomial must be 3x minus 2 times 2x minus 1, which will give us 6x squared, blah, 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 plus 2. Now, notice that this 2 over 3 here, this 2 over 3, the 2 is a factor of 2, right? And the 3 is factor of 6, right?
Yeah.
Okay, so, well, if you see further, this 3 actually later on go here, the 2 later on go here. Now, notice that the denominator always factor of that leading coefficient, right? While the numerator always factor of the constant. Do you see that?
Mm-hmm.
Okay. Now, so yes, that's actually a question I have also before when I learned this part. Why not the factor of leading coefficient over a factor of the constant?
Mhm.
Then my teacher showed me a very similar explanation. Okay, it's more into intuition though. Okay, now let's go back. Let me lasso this. Okay, now let's say, for example, I have px equals to 18x to the 4th minus 10x squared x cubed plus x squared minus 4. Let's say that's our example now. Now, then, according to rational zero theorem, if C is a rational number, then C must be plus minus a factor of 4, which is 1, 2, 4, over a factor of 18. 1, 2, 3, 6, 9. Now, all the possible combinations of this will be plus minus 1, plus minus 2, plus minus 4. Are you with me? I divide by 1 first. 1 over 1, 2 over 1, 4 over 1. Is it okay? And then I divide by 2. That will be plus minus 1 over 2, plus minus 2 over 2, which is 1, and already have that, plus minus 4 over 2.
And the plus minus is because either it's just you're including all the possible combinations.
That's right, because we cannot tell it's positive, negative,
Yeah.
negative yet. We just know that it must be this. But okay, let me go back. But because 2 over 2 is equals to 1 that we already have, 4 over 2 we already have, so I will just ignore it. Okay, going back, what if I divide by 3? So that will be plus minus 1/3, plus minus 2/3, plus minus 4/3, and then plus minus 1/6, plus minus 2/6, but that's 1/3. I'm sorry, 2/6, but that's 1/3. I already have it, right? I cancel that. Plus minus 4/6, but 4/6 is 2/3. I already have that too. I cancel it, and then plus minus
1 over 9.
1 over 9, plus minus 2 over 9, plus minus 4 over 9. Those are all possible rational zeros of this polynomial.
So I guess the way I'm thinking about it is I'm thinking of like what number will multiply to give you 18 and would also give you negative 4. That's not how to think about it.
No.
Okay.
Now, from this list, you see that is 3 in the list.
No.
No, 3 is not in the list, so 3 will not be a 0. Right? 6 is not in the list, so 6 will not be a 0. 5 is not in the list, so 5 will not be a 0. Now, you will see when we try to factor the polynomial later on, we need to find the zeros. And to find the zeros, we'll do trial and error. We'll do guessing game. But when we do guessing game, we will start from those numbers that is more likely to happen. Okay. Now, if from here we see that that if I need to check any rational zeros, I will check something from this list. I will not check 5. Why not? Because it's not in the list. Okay, I will not check 7. I will not check, let's say, 1/4. No, 1/4 will not be a 0 because it's not in the list, in this list, right? 1/4 is a rational number, but it's not in this list, so it won't be a 0. Okay. Now that's how we will use this rational zero theorem later on. Don't worry, on Thursday, I will put everything together. Okay, I still have one theorem that I need to cover though. Descartes' rule of sine, which I believe is one of the lecture videos that we have that I asked you to watch, right? Okay, we already did. The one that I have not done is this guy here. This is the one I have not done. Now, what I will do on Thursday, I will go over this Descartes' rule of sine, and then I will do some problems. Okay, basically, what kind of problems? I will, we start from a polynomial, and then we get all the zeros, and then graph them. Okay, now notice that none of these theorems or rules or fundamental theorem that we have here, none of these theorems that I teach you here give us the zero. No, but it helps us to locate the zero. It helps us to narrow down the options. Okay, now again, you may get really confused right now. Don't worry about it. You are normal. We learn so many things at once. Okay, but you need to learn them anyway. And I would like you to do some suggested problem. Suggested homework from 12.5. I would like you to do number 5, number 7, number 9. Okay, and then 12.4. Actually, no homework from 12.4. 12.3. Number 1 to number 1, number 3, number 9, number 11. I try not to give you too many homeworks because you only have 2 days. 9, number 11, and then number 19, number 21, number 29, number 33, 4.2, 4.2, number 13, number 11, number 13, and then using synthetic division, number 21, 23, 25, 27, and finally 4.6, where we learn the basics so far. Let me write it here. Number 27, 29, 31, 33. I guess that's what I did. Oh, you know what? And then 35, 37 too. 35, Oh, wow, that scares me. 37. Okay, I think that's all. I hope that's not too much for 2 days. Each one of them is quite short, except for 4.6. It will take you quite long time. Yeah, this one will take you quite long time, but this part here, each one of them is actually quite short. And what we will do on Thursday, we'll put these things together. Maybe in the first 1.5 hours, we will discuss maybe 3 problems before I jump to 4.7. Okay, see you then on Thursday. I will have my office hour after this. Okay, so I will stay online and even on the Zoom, even though I don't record that anymore. So if you have questions,